Welcome to the Explainer. Look, if you build neural networks, you probably spend your life optimizing loss functions, right? You import them, you minimize them, and honestly, you completely trust them. But today, I'm going to show you exactly why you've been doing it this way all along. We're going to deconstruct the tools you use every single day to uncover the rigid, undeniable mathematical laws that are actually governing every single model you train.
So let's just dive right into it. Why exactly do you use mean squared error for regression and cross-entropy for classification? Like, are they just these arbitrary mathematical punishments we decided to apply to our models? Maybe just some stylistic choice passed down through PyTorch documentation? No, absolutely not. Today, we're stripping things back to first principles. We're going to see that your loss functions aren't random at all. They are strict mathematical derivations of a much deeper truth.
To really get this, we gotta start with the absolute bedrock of parameter estimation, maximum likelihood estimation, or MLE. Basically, MLE answers the most fundamental question in AI. Given the data I just saw, what should my model's parameters actually be? It all starts with one core concept, likelihood. See, deep learning optimization is really just the process of trying to find the exact weights and biases that maximize this probability across thousands of independent samples. You literally just want the model that makes your specific, observed dataset look as mathematically probable as possible.
But here's the catch. Computing this likelihood creates a massive engineering problem. To find the joint probability of your entire dataset, you've got to multiply the individual probabilities of every single sample together. So think about it. What happens when a computer tries to multiply thousands of tiny probabilities together? Like, what happens when you take a really small probability, let's say 0.1, and you raise it to the power of 100 just for a single batch of data? Let's take a look.
Boom! Zero. It completely zeroes out. This right here is a pure math horror moment for any engineer. It's called floating point underflow. When numbers get too incredibly small, the computer's memory just gives up and truncates them to absolute zero. It destroys your gradients, and it completely ruins your training. And this right here proves exactly why we can't just maximize raw likelihood.
But thankfully, a single mathematical trick rescues this whole operation. We take the natural logarithm of the likelihood. Because a logarithm is a monotonically increasing function, maximizing the log likelihood gives us the exact same parameters as maximizing the regular likelihood. But check out the engineering benefits here. It turns all those tiny multiplications into safe, stable additions, entirely preventing that underflow problem. Plus, it strips away those nasty, complex exponential terms, which makes calculating our derivatives so much easier. And since our optimizers are built to minimize things rather than maximize them, we just flip the sign. We minimize the negative log likelihood. So using a log isn't some stylistic choice. It is a literal engineering necessity that sets up the exact loss functions we code every single day.
Section 1. MLE, the data dictator.
Okay, let's look at how this actually behaves in practice. I like to call MLE the data dictator because it strictly, stubbornly trusts only the data it sees. Imagine you find a biased coin on the ground. You flip it 10 times and it lands on heads 7 times. So what's the probability that this coin lands on heads? Well, the dictator looks purely at that data and says exactly 0.7. Why? Because if the true probability was 0.7, then seeing 7 heads is literally the most probable outcome. MLE blindly picks the exact parameter that makes the observed data look as likely as possible, even if it means heavily overfitting to a super tiny, noisy sample size.
Now let's connect this dictator directly to your code. Watch closely as we derive mean squared error straight from MLE. Suppose we're predicting a continuous value and we assume our data has Gaussian noise. We start with the pretty terrifying-looking Gaussian probability density function. Next, we apply our natural logarithm trick, and immediately those messy exponential terms drop right down into simple algebra. Now here is the deeply satisfying part. Because we're optimizing, we only care about the variables that actually change, right? So we can literally cross out all the constant terms, watch them cancel out. And what are we left with? Highlighted right there in gold, it's the sum of the squared differences between the true y and our predicted y. That is exactly mean squared error. So MSE isn't some made-up metric. It is mathematically identical to Gaussian MLE.
And you know what? The exact same logic applies to classification. When you use cross-entropy loss, you're really just wearing another mask for MLE. When minimizing cross-entropy, your model is quite literally maximizing the log probability of the true one-hot encoded labels under a categorical distribution. You're forcing the model to make those true labels as mathematically likely as possible.
Section 2. MAP, the compromise maker. So the data dictator has one fatal flaw: overfitting. Think about it. If you flip a coin 3 times and get 3 heads, MLE will blindly memorize that noise and assume the coin is heads 100% of the time forever. Let's visually contrast this. On the left, we have MLE, which trusts absolutely nothing but the raw data. To fix this, we need to transition to the right, Maximum A Posteriori, or MAP. This is the compromise maker. MAP uses Bayes' theorem to balance the data's likelihood with a pre-existing prior belief. Like, for example, using your common sense to know that a coin you found in a regular wallet is almost certainly a 50-50 fair coin.
This beautifully illustrates exactly how that works. Notice how these bell curves are interacting. That initial peak on the right is our MLE likelihood. It's whatever the raw data is screaming at us. But now we introduce a prior. That's the second curve, centered at a different belief, maybe somewhere near 0. Notice how, as we multiply the likelihood by the prior to get our posterior, that resulting peak dynamically shifts. The prior is physically pulling the model's parameters away from the noisy extreme edges of the data and anchoring them back toward a much more sensible restrained value.
So what does this visual shifting actually mean for your neural network? Well, let's reveal our second massive algebraic truth. In MAP, we add the log prior to our objective. Let's assume your weights are drawn from a zero-mean Gaussian prior, meaning we fundamentally believe small weights are vastly more likely than massive, explosive weights. We take the log of this Gaussian prior, we drop the constants once again, and what remains is a penalty term based on the squared magnitude of the weights. We end up minimizing our negative log likelihood plus lambda times the squared weights. Guys, this is exactly L2 regularization, or weight decay. Every single time you use weight decay, you are mathematically performing MAP inference.
Section 3. The code we write every day.
Let's pivot away from the pure math on the whiteboard and look at the actual PyTorch code you write every single day. Because honestly, understanding this theory is what separates someone who just copies boilerplate code from an engineer who truly controls their architecture. Look at these PyTorch realities. When you call cross-entropy loss, PyTorch isn't just applying a raw math formula. If you naively compute the log of a soft math, you're going to hit that exact underflow math horror we warned about earlier, and you'll be returning nans by the end of epoch 1. Instead, PyTorch fuses these operations using the log sum exp trick under the hood, specifically to safely compute the MLE. And when you set weight decay in your atom optimizer, you aren't just adding some random penalty, the optimizer is decoupled to apply the exact derivative of that map Gaussian prior directly to your weights.
Let's rapidly fire through where this actually shows up in the wild, because it is literally everywhere. Training a CNN or an LLM like GPT-4 to predict the next token, that's just MLE through cross-entropy over millions of sequences. Training a diffusion model to denoise an image, that's MLE through mean squared error, estimating the mean of a Gaussian noise distribution. What about designing variational autoencoders? The ELBO loss is literally an MLE reconstruction term combined with a MAP prior penalty, the KL divergence.
So the crucial takeaway here is to cement this permanent mental model. Just remember this golden rule. MLE maximizes the probability of the data given the parameters. MAP maximizes the probability of the parameters given the data. One is the dictator enforcing the data's will, the other is the compromise maker balancing the data with a prior belief. Basically, every standard loss function and regularizer you use is just a clever disguise for these two core concepts.
Which brings us to the final, lingering thought of this explainer. We've just proven that MSE perfectly assumes Gaussian noise, and weight decay perfectly assumes a Gaussian prior on your weights. So the next time you tweak a formula or write a custom loss function, I want you to ask yourself, what hidden, rigid mathematical assumptions are you blindly forcing onto your data? Something to think about. Until next time, keep optimizing.